In this video, I will go over your calculus unit for review, the calculator portion of the test. So our first question, let f be a function with derivative defined by this equation here. How many critical values are there? So critical values are when f prime of x is going to equal 0. So what we're going to do is graph this. Okay, cosine squared is the same as cosine of x squared. So the cosine in parentheses, then square it, divided by x minus 2/9, and you could do the fraction thing for our window. Okay, we have a specific interval, so those are going to be our 0 to 10. For my y min and my y max, I'm looking for my zeros. So going from negative 0.5 to 0.5 should be sufficient. So there's 1, 2, 3. Okay, so the 3 locations where it crosses, that's where the derivative is 0. Those are our critical points. So we have 3 critical points. Okay, same equation, and now we want to know how many points of inflection we have. So looking back at our graph, points of inflection are where the second derivative changes signs. So that's on this graph going to be the maximums and the minimums. So we're going to have 1, 2, 3, 4, 5, 6 different inflection points. Okay, if f prime of x equals sine of x and g prime of x equals 1 for all x, and the limit as x goes to 0 of f of x is 0, and the limit as x goes to 0 of g of x is 0, find this limit. Okay, well, if the limits are 0 and 0, that means we're using L'Hopital's rule. So the limit as x goes to 0 of f of x over g of x is going to equal the limit as x goes to 0 of f prime of x over g prime of x. So f prime of x is sine of x. G of x is just 1. So this will be sine of 0, which is 0. Okay, next we have a related rates problem. Okay, it says a rubber cone maintains a conic shape as it is stretched. At the instant when the inner radius of the tube is 3, so I'm going to say r equals 3, and the height is 10, the inner radius is decreasing at a rate of 1 millimeter per second. So dr dt is going to be a negative 1. The height is increasing at a rate of 4. Is the volume increasing or decreasing at this instant? And what is the rate of change of the volume? So our volume is 1/3 pi r squared h. Okay, we're going to take the derivative of this and we're going to need to do the product rule. So dv dt is going to be, I'll take the derivative of this chunk, so 2/3 pi r dr dt times h plus 1/3 pi r squared times the derivative of h, which is going to be dh dt. Now I'm going to plug in the specific values. Is going to be 2/3 pi, my radius is 3, dr dt is negative 1, my height is 4, no, height is 10, sorry. Okay, plus 1/3 pi r squared, then dh dt. Okay, so if we plug all this in the calculator, 2/3 times 3 times negative 1 times 10 is going to be a negative 20. And then 1/3 times 9 times 4 is going to be a positive 12. So we get negative 8 pi. So our rate is negative 8 pi, and it is decreasing. Okay, decreasing at a rate of 8 pi. Okay, a rectangle is inscribed under the curve of y equals 4 minus x squared, with its base on the x-axis and its upper two vertices on the curve symmetric to the y-axis. Okay, we're going to find the maximum area of that rectangle. So our graph looks something like this, which means the rectangle is something like this. Okay, this distance is going to be x, which makes this distance 4 minus x squared. It's going to be the y value there. So my area of that rectangle is going to be the base, which is 2x, times the height, which is 4 minus x squared. So 8x minus 2x cubed. So then we'll take the derivative. Okay, and we're going to set this equal to 0. So 0 equals 8 minus 6x squared. So 6x squared equals 8. So x squared equals 8 divided by 6, which should be 4/3. So x is going to be plus or minus, but we'll just choose the positive, 2 over the square root of 3. Okay, so that's our x value for the location of the maximum. Y is going to be 4 minus 2 over root 3 squared. So that's 4 minus 4/3. So 12/3 minus 4/3 would be 8/3. And you certainly have your calculator for this part. Okay, but what we're asked for is the area. So the area is going to be 2 times the x value times the y value, which is going to be 32 over 3 root 3, or if you just do this all in your calculator, 6.158. In part B, if the x coordinate is increasing at a rate of 0.2 centimeters per second when x equals 1, what is the rate at which the area is changing? All right, so we're going to go back to this equation. I'm going to take its derivative, but this time I'm going to take it with respect to time. Okay, so dA dt is going to be 8 dx dt minus 6x squared dx dt. And then we'll plug in the specific values. So 8 dx dt is 0.2 minus 6. My x is 1. Okay, type all that in your calculator and you're going to get 0.4. This is area, so centimeters squared per second. Right, hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t between 0 and 6 is given in the differentiable function c, where t is measured in minutes. Selected values of c of t are in the chart. So is there a time t where t is between 3 and 6 at which c prime of t is 1.1? Well, this is asking about the mean value theorem. So let's go ahead and find the slope of the secant line. So we're going to have 14.5 minus 11.2 over 3. So 3.3 over 3 is 1.1. Okay, so yes. Okay, and then we're going to justify our answer. So we need to state the hypothesis of the mean value theorem. Since c of t is differentiable, that means C of t is continuous because it must be continuous to be differentiable. Then we can say by the mean value theorem, and then basically repeat this. There is a time t in 3 is less than t is less than 6 at which c prime of t equals 1.1. So basically restating that part. All right, we have an absolute maximum and absolute minimum of the cardioid, r equals 1 plus cosine theta on the interval pi over 3 to pi. So this is an extreme value theorem. We need to check the endpoints and we need to check the critical points. Okay. Well, first we have to come up with our equation. In polar, x equals r cosine theta. So ours is going to be 1 plus cosine theta. So for my endpoints, we're going to be 1 minus cosine pi over 3 times cosine pi over 3. You have your calculator, so you can do it that way, or use a unit circle. Plus. So this is going to be 3 halves times 1 half is 3 fourths, or type it in your calculator. Then we want pi. Okay, the cosine of pi is 0, so this is going to be 1 plus 0 times 0, which is 0. Okay, then we want to find our critical points. So I'm going to go ahead and distribute here. Okay, so I don't have to do a product rule. So we're going to take the derivative of this. So negative sine theta minus 2 cosine theta sine theta. Okay, using the chain rule there. Okay, we're setting this equal to 0. And I'm going to go ahead and move everything to the other side of the equation. Okay, so we want to factor. And then set each factor equal to 0. So we're looking for sine to be 0. That's where our y value is going to be 0. The only location on that interval is going to be pi, which is an endpoint. Cosine equaling negative 1 half, we're looking between pi over 3 and pi, where our x value is going to be negative 1 half. So that's going to be at theta equals 2 pi over 3. So that's our last candidate. So we'll plug this back into our original equation. So 1 plus cosine 2 pi over 3 cosine 2 pi over 3. Well, we already know it's negative 1 half. So this will be 1 minus 1 half times a negative 1 half, which will be 1 half times negative 1 half is a negative 1 fourth. So you can put that information in a chart if you want to. So our 3 candidates are these 3. We want to know what the absolute max and absolute min is. So according to my chart, my absolute minimum on this specific interval is negative 1 fourth. My absolute maximum on this interval is 3 fourths. Okay, we have another related rates problem. A container in the shape of a right circular cone with a height of 6 centimeters and a base diameter of 8 centimeters. Water in the container is evaporating, so the depth is changing at a constant rate of negative 2/5 centimeters per hour. Volume is 1/3 pi r squared h. We're going to find the rate of change of the volume in the water in the container when h equals 4. So our variables we were given was the depth is changing, so dh dt is negative 2/5. My h is 4, and we're trying to find dv dt. Okay, so our volume is 1/3 pi r squared h, but we have nothing involving r here. So we're going to need to eliminate that. Okay, we're told that the diameter is 8, our height is 6. So I can use similar triangles where this is 4 and 6, R and H. So the proportion of R over H will always equal 4 over 6. So R will equal, 4 over 6 is 2/3, so 2/3 H. So in my volume equation, we're going to replace R with this. Okay, do some simplifying here. So V is 4/27 pi h cubed. Okay. Now we're going to go ahead and take the derivative with respect to time. So dv dt, when I multiply this down, we're going to have 4/9 pi h squared dh dt. Then substitute in our variables. So dv dt, we're going to have 4/9 pi. My h is 4. My dh dt is negative 2/5. Okay, if you multiply all this together, that's a negative 128 pi over 45, or approximately negative 8.9, it's a minus, 6 centimeters cubed per hour. Okay, our final equation, our final problem. Write an equation for the tangent line to f of x where x equals 0 with this equation. We always need two things when writing the equation of a line. We need a point and a slope. Okay, so if I plug in 0, sine of 0 is 0, so we have 1 to the 3/2, which is just 1. So our point is 0, 1. For the slope, we take the derivative. We're going to have to do a chain rule here, so we'll do the power rule first. Leave the inside alone. Subtract 1. Then multiply by the derivative of the inside. Okay, then we'll evaluate this at 0. Okay, so sine of 0 is 0, so this is going to be 3/2 times cosine of 0 is 1, so 2. So we get 3, and again, you have your calculator on this part. So my tangent line is going to be y minus 1 equals 3, x minus 0. Okay, which you can leave it like that. We are going to be using it here, so I'll go ahead and distribute this. Is going to be 3x, so we'll have 3x plus 1. So use this to approximate 0.1. Which is just going to be 1.3. So we're using the tangent line to approximate a value. So when would the tangent line approximation be an overestimate versus an underestimate? Okay, there's two cases. It depends on the concavity. Okay, if I have a graph that is concave up, it's going to look like that. If we have a graph that's concave down, it's going to look like this. So if it's concave up, okay, it's going to be an underestimate. is the tangent line is below. Okay, if it's concave up, then our tangent line is going to be an overestimate. So that was your Unit 4 review for the calculator portion of the test.